SCA vendors don't want you to know this, but the scanning part of what they sell you is a solved problem. The hard part was never finding the vulnerabilities, it's knowing which ones matter and how to fix them safely. And that's what this video is all about. Let's jump in. In my last video, I walked through the 3 biggest problems with software supply chain security programs. If you missed that one, I'll link it in the description. But the short version is this. Finding vulnerabilities is easy. Knowing which ones actually matter is hard, and fixing them is risky. Today I'm going to show you practical solutions to each of those problems. And every tool I'm going to show you is either free or already on your machine. So let me walk you through it. The first problem was that SCA tools charge 6 figures or more to do what is basically just a lookup. They read your package manifest, compare it against a database of known CVEs, and give you a list of vulnerabilities. That's commodity work. So here's the fix. Use the OSV-Scanner. It's free, it's open source, and it's backed by the OSV Vulnerability Database, which is one of the most comprehensive available. So let me show you how simple this is. You install it, point it to your repository, and run it. That's it. And a little while later, you get a list of every known vulnerability in your dependencies. It supports most major languages and package managers, including NPM, PyPy, Go, Maven, and more. And you can plug this into your CI/CD pipeline so it runs on every pull request. Now, quick aside here, I actually walked through exactly how to set that up in my DevSecOps Pro course. If you want the step-by-step instructions with labs and templates, I'll drop a link in the description. But the point is, you do not need to pay a vendor for this. The scanning problem is solved. The real challenge is what comes next. So the second problem was that SCA findings are theoretical. Your tool spits out a CVSS score, but that score is typically a worst-case number. It assumes everything lines up perfectly for the attacker, but in your environment, it almost never does. So instead of trusting that score blindly, here's what I recommend. When you get back a finding, whether it's critical or high risk, go read the actual CVE advisory. Not the summary your tool shows you, the actual advisory. Look for the preconditions. In other words, what has to be true for this to be exploitable? Let me show you what I mean. Take this CVE for example. This is an authentication bypass in Paramiko, the popular Python SSH library. CVSS score is 9.8, which is a critical risk. And that sounds bad, but when you actually read all the advisory information, you find out that this vulnerability only affects Paramiko when it's used as an SSH server. If you're using it to make outbound SFTP connections, which is what most people use it for, this doesn't actually apply to you. So here's the process. Step 1, pull up the CVE advisory. The NVD page is a good starting point. Step 2, read through the description and any linked references. Look for phrases like only when, requires, if configured, or when used as. Step 3, build a checklist of what has to be true for this to be exploitable in your environment. For this CVE, that checklist is pretty short. Are we using Paramiko, a vulnerable version of Paramiko, and are we using it as an SSH server? Are we accepting inbound SSH connections on this service? If the answer to either of those is no, your actual risk is close to 0, regardless of what the CVSS score says. And finally, step 4, search your codebase to confirm. Now, you don't need fancy tooling for this. Open up your terminal. Simply use grep or ripgrep to search for how that package is being used. In your IDE, you can use the built-in search to look across your entire project. And if your code is on GitHub, you can use GitHub's code search to find every import or function call across your repositories without even cloning anything into your local environment. For Paramiko, I would search for things like start server, bind, or listen to see if anyone is spinning up an SSH server. If all you find is outbound SFTP connections, you can confidently deprioritize that finding and move on to something that actually matters. This is how you cut through the noise. Not with a fancier tool, but with a 15-minute investigation. The third problem was that fixes look simple but carry real risk. Bumping a version number is a one-line change in code. But if that upgrade introduces a breaking change, you have a new problem on your hands. So here's how you assess the risk before you make the change. Let me walk you through a real example. This particular CVE is a command injection vulnerability in the popular Lodash package. Specifically, it affects the template function. If your application passes unsanitized user input into the variable option of Lodash's template function, an attacker can inject and execute arbitrary code. CVSS score on this one is 7.2, which is high risk, and the fix is upgraded from Lodash 4.17.20 to 4.17.21. Now before you make that change, look at the version numbers. This is a patch release. The third number changed, 4.17.20 to 4.17.21. Under semantic versioning, a patch release means bug fixes only. No new features, no breaking changes. This is the lowest risk category of upgrade. Compare that to a minor release where the second number changes, and that means new features were added, but it should be backward compatible. But a major release where the first number changes, this is where the breaking changes live. So just by looking at the version number, you already know the risk profile of this upgrade. But don't stop there. Go to the project's GitHub page, look for the releases or changelog. For Lodash 4.17.21, the release notes confirm it's a security patch only. It fixes that specific CVE and one other issue of regex DOS vulnerability. No API changes, no behavior changes. That gives you confidence that this upgrade is safe to apply. Now here's the catch. Semantic versioning is a convention, but not a guarantee. Breaking changes can slip into break releases. It happens. So you still need to run your tests after the upgrade. This is not negotiable. But by checking the version bump type and reading the release notes first, you can prioritize the upgrades that are most likely to go smoothly. And that means your developers spend their time on the upgrades that matter, not fighting through risky major version jumps for vulnerabilities that might not even affect them. Okay, so let me bring this together. Solution 1. Stop paying 6 or 7 figures for scanning. OSV-Scanner is free, open source, and it does the job just fine. Plug it into your pipeline and move on. Solution 2. When you get a new finding, read the actual CVE advisory. Build a preconditions checklist. Search your code base. Spend 15 minutes investigating before you spend weeks remediating. Solution 3. Before you upgrade, look at the version bump. Read the release notes. Patch releases are low risk. Major releases need more scrutiny. Use that to prioritize. These are not complicated steps, but they make the difference between a supply chain security program that generates noise and one that actually reduces risk. Now, some of you are going to want to go deeper, and if you're that type of person, I have a solution for you. If you want to see me walk through this entire process live, step by step, I'm running a webinar later this month. It's called Burn Down Your SCA Backlog. I'm going to go deeper on each of these solutions, show you exactly how I set this up, and answer your questions live. Registration is free. I'm going to drop a link in the description. Also, I write about this regularly in my newsletter, the Product Security Playbook. It's where I share my lessons from the trenches and what actually works at scale. Link is in the description. Okay, so if this was helpful, hit subscribe. I put out new videos every week on product security, AppSec, and DevSecOps. Thanks for watching. I'll see you in the next one.